Okay, what we just did was the governing equation in Cartesian coordinate, but we also need the same equation in other coordinate systems. Why? Uh, Here is a point to be made. Um, if you have a geometry that looks like this or like this, it's going to be hard to use that XYZ equation. It's still valid, but it's going to be hard to use to solve it. Remember, we just don't derive equations, we need to solve these equations. So in cylindrical and spherical equations, the spherical coordinate system, I mean, the same governing heat transfer equation looks different. We're going to derive this one now, and this one will be left as an exercise. So in deriving the governing equation in cylindrical coordinate, we start from a cylindrical geometry. And a cylindrical geometry kind of looks like this, of course. And let's say, it's like it could be a pipe in which this is the pipe in which liquid is flowing. And let's say this is hot and this is cold. So there's heat transfer going this way, radially. Okay, the temperatures are not varying circumferentially. So if the temperature is same all along, then there cannot be heat flow because heat flow needs gradient. So we are only interested in this radial flow of energy. Okay, so in this radial coordinate system, heat flux would be written, the Fourier's law is minus k times gradient in the radial direction. So we want to perform energy balance on a shell. So I want you to recap that in Cartesian coordinate we had a control volume like that. Now if we can't use this one here, so we have to match it to the geometry. So instead of this control volume, we're going to have this control volume here. That is the part that you see here. Okay, so this is a shell now. Do you all see this? This is a shell whose inside radius is r and the outside radius is r plus delta r. In the same way that this location is x and this location was x plus delta x. So this is delta x thickness, this is delta r thickness. So it should be r plus delta r. Okay, so here, just like here, we did an energy balance. In minus out plus what is generated should be equal to change in storage. We will do exactly the same thing on this shell. So energy is going in this way and energy is going out this way. So it's going into this phase and coming out this phase, and that's where we're going to do the same energy balance. Okay, so we're going to see how much energy came into this control volume from this way and how much energy came out. We're now going to write the four terms um, in our energy balance: in, out, generated, and change in storage. Um, so remember, our control volume looks something like this. So there is the in term and there is the out term. So this is in, out. So the in term, the energy in is minus K del T del R. So that's a flux, right? So it's joules per meter square per second. Now, which meter square is that? That's the inside area. So if this is a cylinder that goes like that, it's the inside of this cylinder. So this is at R. So the area, the surface area over which heat transfer happens is 2 pi RL. Then the heat goes out through this outer surface area. My terrible drawing there. But this outer surface area, this radius here is R plus delta R. Okay, so then the surface area is 2 pi R plus delta R L. Minus K del T del R at R plus delta R, that's the gradient. So at this point, minus K del T del R is the flux. So the unit of this is again joules per meter square per second, but evaluated at this point, times the area. So this gives me the, the energy, that the rate at which energy is going out. And this term, this one and this one, they're both multiplied by delta T, which means if I open up the bracket, if I expand it, then this term will stand for energy that came in to this control volume over time delta T over the entire surface. And this term is the energy that went out through the outer surface over the entire control volume. And now in this control volume also there can be energy generated, as we already discussed. So if Q is the rate of energy generation, then notice that because this volume is thin, delta R is small, this says that this area that you see, this area is 2 pi R delta R, because 2 pi R is the circumference. So 2 pi R delta R is the area times the length is the volume. So this is the volume. So joules per meter cube times meter cube gives me joules per meter cube per second, and then meter cube cancels, so we have joules per second multiplied by seconds here, that gives me joule. Okay, so in, out, generated, together, because energy came into this and energy came out and some energy got generated in here. As a result of all that, the stored energy here can change, meaning its temperature can change. And that term will be given by, again, mCp delta T. So what is the M? What is the mass of this? The volume, as we already discussed, is 2 pi R delta R times L. And so times density gives me mass. So this part of it is M, and then mCp delta T. Okay? So that is the change in storage. So this is this term here. Okay, so we're ready to start to simplify. So if I divide by 2 pi r delta RL. So I divide everything by 2 pi r delta RL, just like in the past we divided by delta x, delta y, delta z. So if I do that, the L cancels out, 2 pi cancels out, and we are left with this in the denominator, and I rearrange these two terms, the out and the in terms, so that we can write r plus delta r times k del t del r at r plus delta r minus k del t del r at r times r. That's this term here. Plus q is equal to rho Cp del T del T. Simplify, making this shell thickness go to 0. So we're taking the limit. So delta R and delta T, we let them go to 0. Then notice what happens here. We have something, at R plus delta R times, this is like R at R plus delta. So this quantity here is nothing but R del T del R at R plus delta R, right? Because if I evaluate this at R plus delta R, then first on this side we'll get R plus delta R term, and on this side we'll get del T del R at R plus delta R, okay? And notice this term is sort of the same thing, R del T del R, but evaluated at R. K, we're saying K is a constant, so we're not really discussing K. So you can assume that we can take it outside, which we did here, okay? But a quantity at R plus delta R minus the same quantity at R divided by delta R in the limit when delta R goes to 0 is going to give me the derivative, okay? And then we still have this 1 over R here, and of course our K. Q stays as before, rho Cp, and then del T, as del T goes to 0, limit as del T goes to 0, then we get the derivative. Further simplifying and rewriting, just like before, so we have rho Cp del T. You recall this is the storage term, and then this is conduction, and this is generation. I've already thrown out the flow term, so the flow, the convection term is missing because assumed no flow, just to make life easier. Okay, we have done Cartesian and we have done cylindrical. We want to do one more, which is really a special adaptation of these in case of a tissue having blood vessels. Okay, so it's a special adaptation. It's not a separate equation, so to say. Okay, for this special adaptation, let's look at blood flow, blood circulation in the body for a second for heat transfer purposes. So in blood circulation, blood goes from larger artery to the smaller arteries and to the arterioles, back to capillaries, and then small veins to large veins. Okay,
So, so this is the sequence that things happen. So the interesting part is where does most of the heat transfer take place from between the blood and the tissue? Where does the heat transfer take place? So let's look at another slide. So here we have a schematic from literature that talks about how the the blood temperature equilibrates with tissue temperature. So suppose we have a situation where the tissue temperature is lower than the blood. The x-axis is distance along flow path, meaning this distance. Okay, so it's this distance that we are talking about. So um, let's say the tissue is colder than the blood. So the blood starts here and the tissue is here. Okay. Um, when the blood is going through the larger vessels, so here, so in larger vessels, the blood is carrying so much energy, MCPT, right? And you have a lot of flow here and times the specific heat. So it's carrying a lot of energy in this large. So if it's carrying a lot of energy, it will not quickly lose all of it to the tissue. That's very difficult because it has so much energy and it has only this little surface area to lose the heat to the tissue. It only loses through where it touches the tissue. So compared to the amount of blood, the surface area available for heat exchange is less. So the blood stays warm. It doesn't really cool down significantly until it reaches the smaller vessels. So until it reaches somewhere here, then the blood equilibrates with the tissue. So remember I said the tissue is colder and the blood is warmer. So here the blood becomes equilibrate to the tissue. Why? Because in these vessels, the amount of blood flow is much smaller, and so compared to that small amount, the surface area available is sufficient, so the heat transfer is rapid enough between the blood and the tissue, and therefore the blood equilibrates with the tissue. Okay, so the heat exchange basically happens in these smaller vessels. This is the punchline. Heat exchange basically happens in these smaller vessels. And so an example of that could be like blood capillaries in brain. So this is where we can make the assumption that the blood dumps all the heat to the tissue. Okay. However, we cannot make the assumption in a region like this when you have a large vessel. So we cannot make the assumption that the blood equilibrates with the tissue and it gives off all the heat. So the equation that we're about to derive is valid for regions like this and not like this. Okay. So just to remind, then bioheat equation is a special adaptation of the governing equation when we have blood flow in the tissue. Okay, so it's a special adaptation. It's not a new version. So this, if you recall, this was our control volume when we derived the equation the governing equation in Cartesian coordinate. Um, so this is our governing equation in Cartesian coordinate. You remember there's a change in storage term, there's a conduction term, and there's a heat source term. So we have removed no flow term here. Okay. Now you may wonder, oh, what happened to the flow term? We have blood flow. Well, that effect is included in this total source term. How? If the blood is flowing, the energy supplied by the blood is like a source term, because I want you to think this way, that in the smaller vessels, only in the smaller vessels, blood goes in at some blood temperature, let's say arterial blood temperature, but it goes out, goes in at arterial blood temperature, goes out at tissue temperature. So, which means what? If it was warmer, it dumped some heat in this volume. And that is how I will count the effect of the heat carried by the blood. And so how much is that? So if volumetric blood flow rate is VB, so this has three subscripts and superscripts. So V dot, the dot refers to volumetric flow rate, meter cube per second, but it's for blood, so this is blood, okay, and the volumetric blood flow rate is not just meter cube of blood per second, but meter cube of blood per meter cube tissue. So meter cube of blood per meter cube of tissue per second. Okay. Um, so that's this one. So volumetric flow times the density is the mass flow rate. And so that times the specific heat gives you this same term as m dot Cp T minus some T reference temperature. So that is the heat carried by the blood. So it brings in the heat because it's warmer, but when it goes out the volume, then uh, it has equilibrated with the tissue, so it has given off that amount of heat. So I'm going to include that as convection due to blood flow. So this is why we have no other flow term in here. We don't have it. Um, because the effect of blood flow is included in here. Okay. The other term that we have in the tissue, because we are doing a bioheat equation, is the metabolic heat generation, Q. That, of course, is nicely volumetrically distributed most of the time, and it's not a bad assumption at all. So what we are saying is these capillaries are isotropic, making the term same in all directions. So if we are doing a 2D problem, let's say that we have another term in here for the y, uh, this term will stay like this, and what that means is the blood capillaries are isotropic in all directions. So to summarize the limitations of the Bioheat equation, we note that we cannot use the large vessels in the domain, or wherever there are large vessels, we cannot use the Bioheat equation. because when we set up the control volume, we assumed a homogeneous material. Okay, so this may work out for those smaller vessels that are more uniformly distributed, but it's not going to work out for large vessels. So can we not do anything about large vessels? No, there is no problem. We just have to treat the tissue and the solid and liquid regions separately. So in other words, we basically get into a numerical solution. So we have the uh, the liquid region and the solid region. We can do these kinds of problems very easily, but in a numerical solution. So the blood flow term that we saw, data for that are available. For example, in this table, we see a whole bunch of organs for which we have blood flow rate data. As an example, we look at the kidney, and so for kidney, we have 1260 as the blood flow rate per minute, and its mass is 0.3, so we can calculate blood flow rate per unit volume from this.